Okay, so I'm continuing on with the extra topics videos on things that people have asked me about that isn't in the pre-calc curriculum, but is something you potentially might need to know for the SAT2 or for something else that you're doing. Keep in mind, I don't know exactly what's on the SAT2. I know the topic, so I'm just going to teach the topic as I would teach it. But I might be giving you more information than you actually need for the SAT2, or I might not give you all of the information. So if you have like other things that I need to cover, let me know. But this is how, like, if I had to teach this in class, this is the stuff I would cover. The matrices, actually, there is a chapter on matrices in your textbook, except it's not in the physical textbook. It's like an online supplement thing. I don't know if you all have access to it. But you might be able to check, like, either in your textbook there might be a website for it, or you can find the link to it somewhere. I got it from somewhere when I was trying to find it at some point, but it was a very long time ago, so I don't remember how I found it. But it was like either there was a link in the textbook or I just Googled it. In any case, this is from that chapter in the book where I got some of these like graphics from, and then I'm just like doing my own examples with that. So a matrix. Matrix is a rectangular array of numbers, and it really is basically a vector that's magnified. So all the stuff we did with vectors still is going to apply to matrices, just instead of the 2-entry vectors we did, these are going to be a little bigger. So matrices, usually when we write matrices out as variables, we write them as uppercase letters, such as A, B, or C. We can also write it as brackets where it's like the lowercase letter and then I and J as the entry for the row and the entry for the column. And then we write out the actual matrix as like a rectangular bit of numbers. So for example, if I had matrix A, it could be this matrix, like 3, 2, 5, 7, 10, 11, 3, 2, 7. That could be a matrix. We could also have a matrix where it's just like 2, 3, 1, 4, 5, 6. Right. They just make rectangles. So they need to be like a number of rows, a number of columns, and then you fill in all those entries with some number. The way we talk about individual elements, so supposing I wanted to know what 10 is, well, that's lowercase a, and then it's the second row and second column, so it would be 2 and 2 is 10. And you might put a comma in there, especially for the big matrices where 22 might be an actual thing. And you do it with row, then column. So like, for example, this is a first row, third column, 1, 3. And so on. You can name each element. For matrices to be equal, they need to have the same order. Order is the size of the matrix, which is row times column. Row and then column. Number of rows, number of columns. And then every corresponding entry needs to be equal. So if we have matrices that are equal, for example, these two matrices, we're saying they're equal, then that means every entry needs to be equal to each other, which means like -3 and -3, 4 and 4, that works. 5 needs to be the same as y minus 3, and x needs to be the same as 2x plus 2. So when I solve this, I get 8 equals y. I solve this, I get x equals -2. And so when x is -2 and y is 8, these two matrices will be equal. That's like a simple solving kind of problem. Now we're going to go into some operations with matrices. So the first one is matrix addition. Again, these things are very similar to vectors. So we're doing matrix addition just like vector addition, and then we're going to do scalar multiplication just like scalar multiplication with vectors. So if you have matrices, two different matrices of the same size, so the same size, then you get a resulting matrix, again of the same size, where you just add up each entry. So I have a 2x2 matrix here and a 2x2 matrix here. So I'm going to end up with something that's also 2x2, where I take each entry and just add it to its corresponding entry, just like we did with vectors. If I gave you -1, 2 plus 1, 3, then you do -1 plus 1, 2 plus 3, and you get your result. That's what we're going to do. So -1 plus 1, 2 plus 3, 0 minus 1, and 1 plus 2. And that gives us 0, 5, -1, and 3. So you get our addition. In this next one, we have a 3 by 3 matrix and a 3 by 2 matrix. In this case, they're not the same size, not the same order. And so this is undefined. You can't add matrices that are of different sizes. They have to be the same size because we need to have corresponding entries to add up. So when they're not the same size, we're not going to have every entry have a corresponding entry in the other matrix. Scalar multiplication is, again, similar, and this helps us deal with subtraction as well, because scalar multiplication is scaling everything up by a number. You scale every entry in the matrix by that number, and then if you scale by a negative, that negates the matrix. That helps us with subtraction, because if you scale by -1, that makes a negative matrix, right? Negative b is the same as -1 times b, and so if we wanted a minus b, that's the same as a plus -1 times b, just like with vectors. So let's do this problem. We have two matrices, A and B. They are both 3 by 3 matrices, so they're the same size. And we want to find 3 times A and then 3A minus B. So 3 times A is scaling A up by 3. So I need to multiply the 3 into every entry, which means 3 times 2, 3 times 2, 3 times 4, 3 times -3, 3 times 0, 3 times -1, 3 times 2, 3 times 1, and 3 times 2. And that gives us a 3A matrix. Then we want to do -3A minus B. So we want to find the negative B matrix, which is -1 times the B matrix, which is -2, -1, 1, 0, 4, -3, -2, -3, 0. And then 3A minus B would be 3A plus -B, which would be 6, -9, 6, 6, 0, 3, 12, -3, 6, plus -2, -1, 1, 0, 4, -3, 0, -3, -2. And then I add these matrices up. So 6 plus -2, 6 plus 0, 12 plus 0, -9 minus 1, 0 plus 4, -3 plus -3, 6 plus 1, 3 minus 3, 6 minus 2, and I get this matrix as a result. We can also sometimes, to make things more convenient for us, we can factor out scalars from matrices. So like in this matrix, everything is divided by 2, so I can factor out the 1/2. And that way I can deal with whole numbers rather than fractions in my matrix. Sometimes this might be more helpful or more convenient to deal with. We have some properties with addition and scalar multiplication, and the properties are very similar to real number properties or to vector properties. So if we add up matrices, they're commutative, which means A plus B is the same as B plus A. It doesn't matter which order you do it in. They're also associative, which means you can group them up differently and it'll still be the same. Scalar multiplication is also associative, so you can either multiply the scalars together and then scale the matrix, or you can scale the matrix by one scalar and then scale it by another scalar. If you scale a matrix by 1, it stays the same. That's called the identity property. And then you can distribute scalars across matrices, or you can distribute multiple scalars to the same matrix, or you can do one scalar to 2 different matrices. It distributes the same way. So let's try putting those properties into effect. So this problem is 3 times the addition of 2 matrices. We can do this in 2 different ways. The first way is going to be adding up the matrices on the inside. So when I add up the matrices inside the parentheses, I get negative 2 plus 4, 0 minus 2, 4 plus 3, and 1 plus 7. And I scale everything by 3, and I get 6, 21, negative 6, 24. So that's one way. The other way would be to distribute the 3 out, which means I'd get negative 6, 12, 0, 3, plus 12, 9, negative 6, 21. And I add these matrices up, I'll get 6, negative 6, 21, and 24. Either way, it works. You can use these properties. It shows us the properties work because I did it 2 different ways and I got the same matrix as my final answer. Using these properties, we can also solve matrix equations. So we can solve for a variable that's a matrix by using our same method. So we have 3x plus a equals b. Well, so that means we can subtract a on both sides and then divide by 3 or scale by 1/3. And so this is what x is going to be, 1/3. Usually also when I'm doing the manipulation, I try to do it without substituting the matrix in, just because it's a lot of unnecessary writing to keep writing what a and b are every time. So I do all the manipulation with variables, and then at the last step here, I'm going to substitute the actual matrices in. So b is negative 3, 2, 4, and 1. Subtract a from it. And since we know that subtraction is the same as just scaling this by negative 1, I'm just going to do it all combined in one step. So this would be the same as negative 3 minus 1, 4 minus negative 2, 2 minus 0, and 1 minus 3. And then scale everything by 1/3. And that would be what the X matrix is. To check, you can also substitute it back in and see if when you put this matrix in for X, will this all stay true or not. The last operation to look at is matrix multiplication. And this again is like in vectors. The scalar multiplication behave normally, but the multiplying 2 vectors together is slightly different. The same thing happens with matrices. Multiplying 2 matrices together is something slightly different. And in this case, we use the same thing. In vectors, we did dot products. With matrix multiplication, we're going to do a bunch of dot products. So for matrix multiplication, we need to make sure that we have our 2 matrices. These ones are going to be of slightly different sizes. They could be the same size, but they don't have to be. What's important here is that the number of columns in the first matrix needs to equal the number of rows in the second matrix. The result will be a matrix that has the number of rows of the first matrix and the number of columns of the second matrix. So basically it's going to give you the opposite things as what needed to be equal here. So your matrices, usually we write them as rows times column. So when I say like a matrix A is m by n, that means it has m rows and n columns. B has to be n by p, right? So that number has to be the same, where it's n columns, n rows. But these could be different. The number of rows and number of columns could be different. Our result will be an m by p matrix. So for example, let's look at this problem. We have A is this 2 by 3 matrix, 2 rows, 3 columns. And then this B matrix is 3 rows and 2 columns. So the columns and rows match up. So we can multiply these matrices. The result is going to be a 2 by 2 matrix, because those are these numbers, 2 by 2. So let's look at how to multiply. So to multiply these, we're going to do some dot producting. What we're going to do is take, so let me rewrite this down here. 1, 4, 2, 5, 6, and 7, 9, 11, 8, 10, 12. Okay. So multiplying these 2 matrices. and we have a 4x4 matrix we're going to get out of it. So we need to figure out what goes in these 4 spots. So what I'm going to do is take this column and this row and treat them as vectors. So I have 1, 2, 3, and 7, 9, 11. I'm going to dot product these two, which means I'm going to do 1 times 7 plus 2 times 9 plus 3 times 11. And when I add those up, I'm going to get 58. Then I'm going to go on for this one. I'm going to do second column, so first row. I'm basing this off of where this is, right? So this was the first row and first column, so I dotted the first row and first column. This is first row, second column, so I'm dotting first row, second column. And so I get 1 times 8 plus 2 times 10 plus 3 times 12. Then this is second row, first column, so this would be 4 times 7 plus 5 times 9 plus 6 times 11. And then this is second row, second column, so 4 times 8 plus 5 times 10 plus 6 times 12. And when I add all of those up, I'll get 58, 64, 139, and 154. And that would be my multiplied out matrix. So remember again, for matrix multiplication, the number of columns in the first matrix needs to equal the number of rows in the second matrix. And the number of the resulting matrix is going to have the same number of rows as the first matrix and the number of columns of the second matrix. So because of this, supposing you had a matrix that was, let's say you had a 4x2 matrix multiplied to a 2x5 matrix. This is possible because you have 2 and 2. Right? The columns on the first matrix is the same as the rows in the second matrix. Now, if I flip this around, I do the 2x5 matrix multiplied to the 4x2 matrix. This does not work because now I have 4 and 5. Those are not the same number. So multiplication with matrices is not commutative. You can't change the order of it and still get the same numbers. Sometimes that might work, sometimes it's not going to work, and a lot of times it's not going to work. And even if you can multiply it, you'll probably get a different result than what you do the other way. So you want to be careful with matrix multiplication in that aspect of it. So those are operations with matrices. I think that's going to be it for this video. I'll do one more video on using matrices for systems of equations. Again, I'm not sure if you need to know this. I think it's a good technique to know anyway, just to help with solving systems of equations if you ever come across those. So I'll do a video on that.